The objective here is to explain what the IEEE 754 standard establishes using binary examples. So let's start here. A float basically stores numbers in scientific notation. And if you're coming from a programming background, you've probably heard of a float as a data type. You've probably seen it as a decimal number like this in code 3.41 or whatever. But this particular video was inspired by my series on the Intel manual, so I thought I'd go down to the binary level. So at the binary level, we have this 754 standard. It's a technical standard, and its title officially is Floating Point Arithmetic, because it'll show a little bit more than just like the format of the bits, what they should be. And we'll get into that a little bit later, but right here I just want to point out that this was established in 1985. So this is long after computers have already been around. There was a lot of controversy over this and a lot of arguments, but in the end we ended up settling on this 754 standard. So before I show you any of this, I thought I'd challenge you. Why don't you design your own standard? Like if you had to represent scientific notation in binary, how would you do that? When I've taught students how 2's complement works for making negative binary numbers, I usually ask them to come up with their own invention first. And that really pays off when they come up with something that's not 2's complement, because no one ever thinks of that right away. But it really pays off when they look at something like what you're about to see with these floating point formats, as in single precision and double precision formats. So you could pause here if you want to invent your own. And in case you're wondering what is scientific notation, so let's recap. It really is a method for writing, and it's for really big or really small numbers. Simply called scientific notation because it's usually seen in scientific work. So you can imagine trying to represent the size of an atom or the mass of the sun. So remember, the big point of scientific notation is actually to save space, but sometimes you lose precision because of that. But first, let's go ahead and just really think about what it means to save space. Here's a dumb example. If I have the number 1234 and instead I try to represent it in this way, well, that's kind of dumb because here's 4 numbers, here's 3 numbers. That's more than the original 4 numbers I was representing, so not a good example. The not dumb one over here, you have 6 numbers and then we boil it down to 5, and as you can imagine, the bigger the number, the better it is to use scientific notation. Maybe you see numbers like this in grade school because you're practicing this whole concept, so the teacher's just taking it easy on you. But as you can see right here, it says depends. So we have this super huge number, and I only use 4 digits here, and this is going to be called the significand. Well, whoops, I lied to you right away. This is the significand, and the idea of floating point, I could bring that up right now. Here's the little decimal point, or in the way we'll look at it is it's going to be a binary point, right? This little point, it could float between any of these numbers. So the way we store the number, we have a lot of options. So again, this part is called the significand, and then technically this is the mantissa, or the fraction, everything that's to the right of the decimal. Oh yeah, the point is, it depends on your needs. Maybe you do want to show every single digit, because when you're doing it like this, you're going to lose this precision right here. These numbers get lost and they turn into zeros, and depending on the context of your work, that might be perfectly fine. Okay, so again, go ahead and pause if you wanted to invent your own system first. But here, let me go ahead and summarize the 2 biggest reasons they had to create a standard on it. Basically, the standard addressed many problems, but the 2 big ones is reliability and portability. Computers were using floating points since 1941. This computer is called the Z3, and this particular picture is of a replica. The idea is not new, it's just the way we all agreed to standardize it. That's relatively new, 1985. So I gotta know, what were those 2 big problems we were having with multiple standards? If we go back, reliability, but to me, the portability one was the more important one. I think you could always test your way out of reliability. Well, here's our first look at the actual format, and you will see the term single precision, double precision. This is 64 bits, and this is 32 bits, so pretty straightforward. And in this particular picture, I like that they indicate a little Indian here, but big Indian over here. So I think that's really important because not all architectures use the little Indian style. But regardless of the architecture, the leftmost bit will still have the same meaning. So let's look at that meaning. Here we are. The leftmost bit is the sign bit, so positive, negative. And then the next 8 bits is the exponent, or the next 8 bits for single precision. It looks like our exponent could be even larger with 11 bits here, and when we get to the bias part, that means we'll need a different bias. I'll get to that in a second. For now, the last part you need to see is the significand or significant. And yes, I think this is a strange order to use as a format, but you get to it pretty quickly, especially after I show you my example on Stack Overflow. But before we leave this slide, I just want you to know if you hear somebody talking about the IEEE, and yes, that's triple E's, the Institute of Electrical and Electronics Engineers. I guess there's enough difference between an electronics engineer and an electrical engineer. Anyways, when you hear somebody talk about the IEEE 754 standard, they are primarily talking about how you write down scientific notation in bits. So they basically mean that you're going to write your sign first, then your exponent. Just make sure you know what an exponent is. That is that part right here, whatever you're raising the base to. But for us, our base is going to be a 2, and we can't use decimal numbers like 2, 3, 4, 5, etc. We'll have to only use ones and zeros. So this is actually more like what we need to focus on. But after the exponent comes what's called the significand. And this is a bad example to look at to really wrap your mind around the significand. We'll get to that in a second. Right here, probably the most complex thing to wrap your mind around, the whole concept of a bias. So the exponent comes with this bias because there's no sign bit for the exponent. Remember when we were talking about having really big or really small numbers? Really small numbers need a negative sign in front of them because you're moving that decimal to the left instead of the right. But the number itself can also be positive or negative. So rather than create 2 signs, this standard is going to use a bias. And the bias is a constant, as you can see it right there. It's a constant that you subtract from the exponent, whatever value you're looking at right there in binary. So in the computer science world, I think it'd be okay for you to think of subtracting anytime you think of bias, but technically that word could just mean some sort of change to a number. Not sure what life is like for the mathematicians, but let's go over a couple examples here. For us to decide what a good bias is, we'll simply need to know how many bits the stored exponent has. So it's a straightforward process. If we have 8 bits, it'll look like this. If we add 4 bits, it'll look like that. Do you see a pattern here already? If you were to break out your pencil and do the math, these numbers will add up to 127. So we need to subtract 127 from whatever 8-bit value we see in the exponent section of a floating point number. This will give us a range of negative 127 to positive 128. Now don't be silly like I was and look at a number like this and think it's different. I mean, 0, 0, 1, 1, 1, 1. Okay, so this is still 127. Just because I put 2 zeros there didn't matter. How about this number? Is this 127? Yes, it is. How about this number? Just because there's 4 zeros in the beginning doesn't mean it's necessarily different. We have to count the number of ones. And in this case, I tricked you because this only has 6 ones versus the 7 ones in the other 2 numbers. See how binary is only good for computers to read? Alright, so the 1 in front of the significand is implicit, so that means it's not really there. That's because we will always need a 1. Using binary numbers, we just always need a 1, at least one here to the left of the decimal. And to quickly summarize why, because if it is a number smaller than 0, then this floating point, this point, will need to float over here to the left. And then that's okay, we have all the zeros we want over here. Alright, so let's jump back up over here. If you have this number for your significand, in actuality, you have just this number. See how we still have those two ones next to each other? And personally, I like to write it like this because the parentheses is just reminding me that it doesn't actually exist at the hardware level. But the wiring is done in a way where it makes sense. And then notice that I just cut off these last 3 zeros because just like in the trick before, we don't need extra zeros to the right of the decimal, just like we didn't need extra zeros to the left when the decimal is over here. Okay, so we're almost to the good part. Let me just say this thing about a concept called NaN, that stands for not a number. We, well, have a couple special values. One was signal infinity, and we actually have a negative and positive infinity. And then there's two other scenarios for these things we call not a number. There's QNANs and SNANs, but this knowledge is all beyond what I want to accomplish with the video. But just for fun, if you did want to make an infinity, you would put all ones in that exponent area. Alright, so let's go to my Stack Overflow answer where I did some nifty tricks to help everybody understand. Make it bigger for you to see, and as you can see in my tab, I had to look up what IEEE stood for. That's such a hard thing to remember. But anyways, somebody asked what is a bias, or what is a bias value of a floating point number, and essentially they ask how does this help determine if the exponent is negative or positive. So after a few answers, I came down here, answered kind of late, and I said to specifically address your confusion. An exponent can seemingly become negative because of the bias, but that's not always necessarily true. It depends on the exponent. My example is if you see 125, and then you're going to do this unbiasing it by subtracting 127, well, that new exponent is actually negative too. And so then you might be wondering, well, how do I make 0? Well, in the exponent range, I just have to make the number 127. Whoa, and I don't know if you saw that, but I accidentally miscalculated right here, so I had to edit the post. But this number right here is 127. So to show the number 0, this is it. And I wrote that it's funny that this is 0 because you see all those ones. And let's not forget, we're talking about 32-bit floating point numbers, and this is referred to as single precision. Right now, we've already gone over this. The tricky part is right down here, and I think I illustrated this pretty nicely. So you have all these binary numbers. This section right here is the exponent. So after you subtract your 127, it actually kind of goes up here. And then you can convert this and do better math and feel better about that. This number right here is 124, so when you subtract 127, you'll get negative 3. And so now we look at this huge number, or maybe simplify it. So we look at this number, and we need to move the decimal. Okay, the decimal is actually right here. We move the decimal to the left. How many times? Well, 3 times, just like in normal scientific notation, all because we're going with base 2 instead of base 10. So our final number, 0.001010, well, I could get rid of that last one. And don't be confused because you see 2 ones right there. There wasn't one here because, again, that one that is here is implied. And also I should say, if you don't know how binary numbers work to the right of the decimal, it's pretty easy. This is 1/2, then 1/4, then 1/8. And if these were all ones, you would just add 1/2 plus 1/4 plus 1/8. There's lots of videos out there on how to do that. But the last point I want to make here is that we could easily have this same number. Here's the number in decimal form. This is the binary form. So we could have this number easily be a negative number if we simply made the first bit a 1. As you can see up here, it was a 0. 0 means positive. So that was my last point. These ones are just fun. Here's the infinity ones I was talking about. But let's get back to the slideshow. And to tell you the truth, that's pretty much the lesson because we've covered what the 754 standard establishes. I can mention some more details real quick. The standard will talk about the interchange formats, and that's encodings using bit strings that may be used to exchange floating point data in an efficient and compact form. So there's some trickery that can happen just because that's how you transfer data. The more compact or compressed data is during a transfer, the better, and thus we come to a rounding rules section. They will specify different ways to do that. There's an exception handling. I got a video on that, and of course in the Intel manual there's several details to talk about in terms of exception handling. But these are just details about crazy scenarios, like if somebody was to try to divide a float by a zero, or if there is some sort of overflow or an underflow. All types of exceptions can arise. So if you did that part in the beginning of the lesson where you created your own way to store a floating point number, or I should say a scientific notation in a binary form, if you went ahead and did that and you're really proud of your work, I would just say good luck getting acceptance, because that is what dominates hardware today, that style. And if you haven't checked it out already, go ahead and look at some of those videos on the Intel manual I'm creating. Though they're a little dry, I think they're pretty educational. Like if you really want to understand low-level x86 architecture, I think that's a good place to start.